Dinosaurs ruled until the sky fell. What if I told you that mammals, including your distant ancestors, were hiding in the shadows for over 100 million years, waiting for their chance to inherit the Earth? The dinosaurs' extinction marked our beginning. In this documentary, we'll take you on a journey from the final days of the dinosaurs' reign to the moment everything changed. Like a peaceful stage before a dramatic final act, we'll reveal what happened when the Chicxulub impactor struck Earth. Using cutting-edge CGI and the latest scientific findings, we'll show how this catastrophic event generated thousand-kilometer winds, global wildfires, tsunamis, and an impact winter that blocked the sun for years. Paradise before the fall. Our camera soars across a vast prehistoric landscape, revealing a world at the height of its splendor. Late Cretaceous North America spreads before us, a mosaic of environments brimming with life. Lush forests of conifers and early flowering plants carpet the land, divided by winding rivers that flow toward ancient seas. This is Earth 66 million years ago, a planet ruled by giants. A herd of Triceratops moves methodically through a flowering meadow, their three-horned faces occasionally rising to scan for danger as they graze. These multi-ton herbivores travel in family groups, the largest adults positioned at the perimeter, forming a protective barrier around juveniles and calves. Their powerful beaks efficiently clip vegetation while their specialized dental batteries, rows of teeth working together like natural scissors, process tough plant material with remarkable efficiency. The ground vibrates subtly, causing the Triceratops herd to tighten formation. Through the tree line emerges a lone Tyrannosaurus rex, its muscular form moving with surprising agility despite weighing over 7 tons. The predator assesses the defensive formation and strategically retreats, conserving energy by seeking easier prey. This careful calculation reflects millions of years of evolutionary refinement. Predator and prey locked in an ancient dance. Overhead, the skies belong to another dynasty. A small flock of Quetzalcoatlus, with wingspans stretching nearly 36 feet, rides thermal currents with minimal effort. These pterosaurs have mastered aerial navigation, using their elongated fourth finger to support wing membranes that provide incredible lift. Their extraordinary anatomy represents one of nature's most successful experiments in flight engineering. The late Cretaceous was sculptured by dinosaurs, explains Dr. Victoria Arbour, paleontologist at the Royal BC Museum. Every ecological niche had been refined through evolutionary processes. The massive herbivores shaped plant communities through selective feeding, while apex predators regulated populations. This sophisticated network of ecological relationships achieved remarkable stability, creating a world where life flourished with breathtaking complexity. The camera pans across a coastal floodplain where a group of duck-billed Edmontosaurus moves through shallow water. Their broad, flattened snouts function as efficient feeding tools, straining vegetation from the water. Each animal processes hundreds of pounds of plant material daily, their specialized jaws containing up to 800 teeth that continuously replace themselves throughout their lifetime. Dinosaurs engineered entirely new ecological niches, continues Dr. Arbour. Consider hadrosaurs like Edmontosaurus. Their complex dental structures allowed them to process plant material with unprecedented efficiency. This opened new dietary pathways and created novel interactions that enriched the entire ecosystem, like threads in a tapestry. Each species strengthened the whole. In a dense forest, smaller dinosaurs navigate the undergrowth. A pack of Dromaeosaurus, feathered predators roughly the size of wolves, moves with coordinated precision. These agile hunters possess remarkable problem-solving abilities, using vocalizations to communicate complex hunting strategies. Their enlarged brain cavities suggest cognitive capabilities far beyond simple reptilian instinct, evidence of sophisticated social behaviors. The scene shifts to the ancient Gobi region, a dramatically different landscape where evolution took unique pathways. Here, Protoceratops, distant relatives of Triceratops, but much smaller, thrive in arid conditions. Their beaked mouths efficiently process tough, drought-resistant vegetation, while their reproductive strategies, laying multiple eggs in carefully constructed nests, provide population resilience during challenging environmental periods. What made dinosaurs remarkable was their ability to specialize for specific ecological conditions while maintaining adaptability, Dr. Arbour explains. Consider Ankylosaurus, with body armor specialized to withstand attacks from the largest predators. Yet these heavily armored animals thrived across multiple environments and climate zones. This balance between specialization and versatility explains their 160 million year dynasty. The camera follows a small rivulet down to a vast floodplain where a herd of Alamosaurus, enormous sauropods reaching lengths of 70 feet, browses on treetops. These giants represent the pinnacle of herbivorous adaptation, their long necks allowing access to vegetation unreachable by other species. Their massive size serves multiple evolutionary functions, deterring predators, enabling efficient digestion, and providing thermal stability. In shallow seas bordering the continents, mosasaurs patrol the waters. These marine reptiles, reaching lengths of 50 feet, have become the ocean's apex predators. The camera captures a mosasaur surging upward to capture a flying pterosaur that ventured too close to the water's surface, demonstrating how predatory relationships crossed environmental boundaries. The Cretaceous world was an interconnected system, Dr. Arbour notes. Nutrient flows between marine and terrestrial environments created feedback loops that sustained biodiversity. Dinosaurs were integral components of planetary systems, like musicians in a grand orchestra playing a symphony of life that had evolved over millions of years. The camera pulls back to reveal different dinosaur communities across separated landmasses. In South America, unique predators like Carnotaurus, with its distinctive bulldog-like skull, hunt specialized prey. In Antarctica, then connected to Australia, dinosaurs have adapted to polar conditions with enhanced night vision and possible seasonal metabolism adjustments. This worldwide dominance wasn't achieved accidentally. The Mesozoic era witnessed multiple extinction events that dinosaurs weathered through evolutionary flexibility. Each crisis eliminated less adaptable species while creating opportunities for survivors to diversify into vacated ecological niches. The camera provides a glimpse of a small, furry creature scurrying between dinosaur feet, one of the early mammals that would later inherit the Earth. For now, these warm-blooded pioneers remain marginal players, unable to compete directly with the dinosaurian masters of the planet's ecosystems. The scene shifts to a perspective from space, showing Earth rotating peacefully. But beyond the planet's fragile atmospheric envelope, something moves against the backdrop of stars, a dark object following a trajectory established millions of years earlier through cosmic chance. Silently, inexorably, it continues its approach. A cosmic bullet. That silent traveler represents more than just a cosmic interloper. Lurking beyond Jupiter's orbit in the outer reaches of our solar system, this particular asteroid belongs to a rare class that would ultimately transform Earth's evolutionary trajectory. Though such carbonaceous chondrites make up a substantial portion of space rocks in our solar system, they account for only about 5% of meteorites that reach Earth's surface today, making it a relatively unusual cosmic visitor. As we track this ancient wanderer through the void, its scale becomes apparent. Measuring approximately the size of Mount Everest, the asteroid's silhouette stands in stark contrast to the backdrop of distant stars. Its journey began millions of years earlier in the cold, distant regions past Jupiter, a place where few asteroids escape from. Yet through some cosmic chance, this particular rock found itself on a collision course with a third planet from the Sun. The asteroid's velocity increases gradually as Earth's gravity begins to exert its inexorable pull. What was once a distant object drifting through space now accelerates dramatically, gathering momentum until it reaches a staggering 72,000 kilometers per hour. At such speeds, the kinetic energy contained within this mass becomes almost incomprehensible, a cosmic bullet carrying the destructive force of billions of nuclear weapons. Looking deeper into its composition through scientific visualization, we see this asteroid contains a distinctive mixture of water, clay minerals, and organic carbon compounds, signatures of a primitive solar system material that formed in the frigid outer reaches beyond the gas giants. These carbonaceous chondrites preserve chemical snapshots from the early solar system, carrying within them the building blocks that would later become crucial to life itself. Carbonaceous chondrites constitute only about 5% of meteorites that fall to Earth despite being common in space, explains Dr. Eliza Thompson, astronomer at the International Asteroid Research Coalition. This discovery provides crucial insights into the origins of the asteroid and its journey to Earth, helping us understand the nature of what we now call the Dino-Killer, the harbinger of extinction that approached without warning. What makes this particular finding so significant is the novel technique researchers employed to confirm the asteroid's origins. As Dr. Thompson explains, by analyzing the isotopic composition of the element ruthenium found in the geological layers marking the debris from the Chicxulub impact, we could confidently trace the ruthenium back to the asteroid itself. Ruthenium is not uncommon on asteroids, but is extremely rare on Earth, providing irrefutable evidence linking the impactor to the ensuing mass extinction. A data overlay appears, plotting the asteroid's inexorable trajectory toward Earth. The collision course was set millions of years ago, with each passing moment bringing it thousands of kilometers closer to its target. The mathematical certainty of its approach contrasts sharply with the complete ignorance of Earth's inhabitants. The analysis of ruthenium isotopes allowed scientists to distinguish between the two main groups of asteroids. Dr. Thompson continues. There are C-type, or carbonaceous, asteroids that formed in the outer solar system, and S-type silicate asteroid from the inner solar system near the Sun. This study confirmed that the asteroid that triggered the mega-earthquake precipitated a global winter and wiped out the dinosaurs and most other life was a C-type asteroid that formed beyond Jupiter. The scene cuts between the asteroid's approach and the vibrant Cretaceous landscape below. A group of duck-billed hadrosaurs wades through a shallow estuary, using their remarkable dental adaptations to process vegetation. Nearby, a small pack of predators moves through underbrush, unaware that their evolutionary story would soon end. In coastal waters, marine reptiles continue their ancient dance of predator and prey. None of Earth's inhabitants possess the capacity to comprehend what approaches from above. No early warning systems, no space agencies, no telescopes tracking potential extinction-level events. The planet continues its rotation, blissfully unaware of the cosmic bullet aimed directly at it. In a tragic cosmic irony, this composition reveals that these carbonaceous chondrites contain organic compounds and water molecules that were essential ingredients for life on early Earth. The same class of asteroid that may have delivered life-giving elements to our planet billions of years earlier would now deliver extinction to its dominant species. A simulation shows what would happen if the asteroid had missed Earth entirely. The dinosaurs would likely have continued their evolutionary journey, perhaps for tens of millions of years more. Mammals might never have had the opportunity to diversify into the ecological niches left vacant. The entire trajectory of life on Earth hinged on this single cosmic encounter. As the asteroid enters the outer reaches of Earth's gravitational influence, its path becomes increasingly locked. Any small deviations in its trajectory that might have caused it to miss the planet entirely have long since passed. The mathematics of orbital mechanics now dictates an unavoidable conclusion. The devastating power contained within this celestial visitor comes from both its impressive size and tremendous velocity. The energy of impact scales with the square of velocity, meaning that doubling the speed quadruples the energy. At 72,000 kilometers per hour, the potential for devastation exceeds anything in human experience. The camera perspective shifts now, moving from the cold emptiness of space to the surface of late Cretaceous Earth. In what would later become Mexico's Yucatan Peninsula, life continues its daily rhythms. The ground teems with insects. Plants reach skyward, converting sunlight into energy through the same photosynthetic process as their descendants would use 66 million years later. Then, almost imperceptibly at first, a new point of light appears in the daytime sky. Unlike the familiar sun, this light grows steadily brighter with each passing hour. What begins as a barely noticeable star-like point soon transforms into a brilliant object that outshines everything except the sun itself. Had any creature possessed the cognitive capacity to understand what this light represented, there would have been no escape. The asteroid's approach, now visible from Earth's surface, marks the beginning of the end for the Mesozoic world order. Within hours, the light will transform into an incandescent fireball streaking across the sky, signaling the arrival of Earth's most catastrophic day in 100 million years. The moment of impact. Within hours, that incandescent fireball transforms into something more catastrophic than any living creature on Earth had ever witnessed. An astronomical reset button hurtling directly toward the pristine coastline of the Yucatan Peninsula. The geological features of this specific impact site would amplify the devastation in ways that would forever alter Earth's evolutionary trajectory. The tranquil waters along the Yucatan shoreline ripple gently under the prehistoric sun. Palm-like cycads sway in the warm breeze. The shallow sea teems with marine life, completely unaware of the approaching doom. This peaceful scene represents the final moments of the Mesozoic world as it had existed for millions of years. Above, the atmosphere begins to glow. The once tiny point of light now dominates the sky as the asteroid tears through the upper atmosphere. Air molecules in its path compress and heat to temperatures rivaling the sun's surface. What was once solid rock now partially ablates, the outer layers vaporizing in a blinding display of thermal energy as friction builds against the increasingly dense atmosphere. But unlike smaller meteorites that completely burn up during atmospheric entry, this mountain-sized object maintains most of its mass during its brief atmospheric transit. The fireball stretches across the sky, casting eerie shadows across the landscape below, a harbinger of the catastrophe to come. What made this impact particularly devastating was the precise angle of impact combined with the unique geological composition of the Yucatan Peninsula, explains Dr. Mira Gonzalez, impact specialist at the Chicxulub Research Institute. These factors created a perfect storm of environmental consequences. Our visualization shows the critical moment. The asteroid strikes at an angle between 45 and 60 degrees relative to Earth's surface. This steep angle proves catastrophic, maximizing both penetration depth and energy transfer. Had it struck at a shallower angle, more energy might have dissipated in the atmosphere. A steeper, more vertical angle might have kept the ejected material more localized. The moment of contact unfolds in our high-fidelity CGI reconstruction. As the asteroid slams into Earth, the immediate transfer of kinetic energy creates temperatures exceeding 10,000 degrees Celsius. This extreme heat instantly vaporizes the asteroid itself and a massive volume of Earth's crust at the impact site. The physics of this collision operate on scales difficult to comprehend. The energy transfer blasts out a cavity approximately 100 kilometers wide and 30 kilometers deep in mere seconds. The visualization shows a cross-section view as the asteroid penetrates deep into Earth's crust, displacing billions of tons of rock. A scientific overlay appears, displaying the energy calculations, equivalent to 10 billion Hiroshima bombs detonating simultaneously. This concentrated energy radiates outward as seismic waves, thermal radiation, and a rapidly expanding shockwave of superheated air and vaporized material. For a moment, our visualization pauses, allowing viewers to absorb the sheer magnitude of destruction unfolding across the prehistoric landscape, a cosmic reset button pressed with devastating force. The specific location of impact dramatically amplified its deadly effects, Dr. Gonzalez continues. The Yucatan Peninsula's geological composition contained high concentrations of sulfur-bearing rocks, particularly anhydrite, a calcium sulfate mineral. Our animation highlights these sulfur-rich rock layers as they vaporize upon impact. The overlay shows the chemical transformation as intense heat converts solid anhydrite into gaseous sulfur dioxide, releasing an estimated 67 billion tons of sulfur compounds into the atmosphere. This sulfur component was crucial to the extinction event, explains Dr. Gonzalez. When these compounds reacted with water vapor in the atmosphere, they formed sulfate aerosols that blocked sunlight for extended periods. This prolonged global cooling created an impact winter that devastated ecosystems worldwide. The animation continues, showing the formation of the Chicxulub crater in dramatic cross-section. First, the initial cavity forms as material vaporizes and ejects. Then, within minutes, gravity pulls back the displaced rock around the rim. This rebound effect creates a central peak rising from the crater floor, followed by multiple concentric rings rippling outward, features still detectable today after 66 million years. The Chicxulub impact created what we call a complex crater with multiple rings, Dr. Gonzalez notes. Its final diameter stretched between 180 and 200 kilometers, making it one of the largest preserved impact structures on Earth. Our visualization zooms outward, showing the full crater forming across the Yucatan Peninsula. The impact breached multiple geological layers, each contributing different materials to the deadly atmospheric cocktail being created. The 45 to 60 degree angle directed more ejected material toward the north and northwest of the impact site. This directional aspect sent disproportionate amounts of debris across what would become North America, explains Dr. Gonzalez. The angle also determined how energy dissipated through Earth's crust and how efficiently the sulfur-bearing rocks were vaporized. The visualization now shows the immediate aftermath as a shockwave of superheated air expands outward at supersonic speeds. This wall of heat and pressure flattens everything in its path, trees, animals, any structure unable to withstand winds exceeding hurricane force by orders of magnitude. Simultaneously, seismic energy, equivalent to a magnitude 10+ earthquake, propagates through Earth's crust. Our cross-section view shows these waves triggering secondary earthquakes, landslides, and volcanic activity across the planet. In the surrounding waters, our animation shows the displacement, creating an initial void where the asteroid struck, followed by a catastrophic rebound. This generates tsunami waves hundreds of meters high, racing toward coastlines throughout the region. The intense heat triggers chemical reactions in the atmosphere, creating nitrogen oxides from atmospheric nitrogen. These compounds, with the vaporized sulfur, begin forming acids in the atmosphere, setting the stage for highly acidic rainfall. What's remarkable about the Chicxulub impact, Dr. Gonzalez concludes, is how it created a cascade of environmental effects, each building upon the others. The immediate destruction began a complex chain reaction that ultimately reshaped Earth's biodiversity. The first hour, shockwaves of destruction. That cascade of destruction unleashed forces so powerful they rewrote the physics of our planet within minutes. When the Earth itself behaves like a liquid upon impact, temporarily losing its solid structure, the resulting shockwave obliterates the very concept of landscape. Imagine a circle of annihilation expanding outward from ground zero at speeds faster than sound itself. The initial shockwave, born from the asteroid's kinetic energy transfer, raced across the land and water at supersonic velocity. It was a wall of pressure so intense that anything in its path faced instantaneous destruction. Within the first few seconds, the energy radiating outward created pressures and temperatures that fundamentally altered the state of matter itself. The most immediate consequence was an air blast that generated hurricane-force winds exceeding 1,000 kilometers per hour. These winds were powerful enough to completely scour the landscape. Forests that had stood for centuries were flattened instantly, completely leveled as if they had never existed. The contours of the land itself were reshaped as the blast wave stripped away soil, plants, and smaller geological features across southern and central North America. The seismic effects of the impact propagated through Earth's crust in all directions. This was one of the most powerful seismic events in our planet's history, registering a magnitude of 10 or higher on the Richter scale. This magnitude exceeds any earthquake in recorded human history by several orders of magnitude. The ground shaking wasn't limited to the impact region, but would have been felt globally. The seismic pulse traveled through the Earth's interior, causing the planet's crust to heave and buckle. Landslides were triggered on every continent, as unstable slopes collapsed under the intense vibrations. Mountain ranges shuddered, sending cascades of rock and debris into previously tranquil valleys. Underground water systems were disrupted, causing geysers and springs to erupt in regions thousands of kilometers from the impact site. While terrestrial environments were being devastated by wind and seismic forces, the oceanic response was equally catastrophic. The initial impact blasted an enormous cavity in the Earth's crust, a temporary void 100 kilometers wide and 30 kilometers deep. This massive displacement of the seafloor generated a mega tsunami unlike anything witnessed in human history. Imagine a wall of water hundreds of meters high, radiating outward from the Gulf of Mexico. These tsunamis utterly reshaped coastal areas. The energy contained in these waves completely eroded coastlines, deposited sediment far inland, and permanently altered oceanic floor features. The impact and resulting tsunamis transported 48,000 cubic miles of sediment across the Gulf of Mexico, burying portions of Mexico and the Caribbean under hundreds of feet of debris. The mechanics of this tsunami went beyond typical wave formation. The impact temporarily removed the distinction between solid earth and liquid ocean, causing both to behave as a unified fluid medium. As the crater rebounded from the initial compression, it sent ripples through both land and sea that converged and amplified each other, creating tsunami waves that grew larger as they traveled. To visualize this destruction sequence, consider what would happen if you were standing at various distances from ground zero during the first hour. Within a 500-kilometer radius, survival would have been virtually impossible. The initial blast wave would arrive within minutes, bringing winds that could pick up and carry objects as large as vehicles. The intense heat following closely behind would ignite any flammable material not already destroyed by the wind. At 1,000 kilometers away, you would have approximately 15 to 20 minutes before experiencing the first effects. The ground beneath your feet would begin trembling, building rapidly to violent shaking that would make standing impossible. Minutes later, the pressure wave would arrive, still carrying winds strong enough to flatten structures. In coastal regions, you might witness the ocean initially receding, the deceptive prelude to an approaching tsunami wall taller than most natural features. What's often overlooked in discussions of the Chicxulub impact, explains Dr. Gonzalez, is the sheer violence of those initial 60 minutes. The environmental effects began with an hour of apocalyptic fury that few scientific models could fully capture until recently. Even at 5,000 kilometers from the impact, you wouldn't escape the consequences. The seismic waves would arrive first, causing significant ground movement. Within an hour, strange atmospheric effects would appear as the pressure wave disturbed the air above. By the end of the first hour, the leading edge of ejecta, superheated material launched into suborbital trajectories, would begin raining down, igniting what would become global wildfires. This complex choreography of destruction, seismic waves, air blasts, tsunamis, and ballistic ejecta, all operated on different timescales and physical principles, yet all originated from the same singular event. Each disaster amplified the others, creating feedback loops that intensified the devastation. Mysterious seismic aftershocks would continue for years, their unusual patterns puzzling any survivors. The most remarkable aspect was the complete transformation of the environment within mere minutes. Areas that had been verdant forests or coastal plains in the morning became unrecognizable wastelands by mid-afternoon. The speed of this transformation left no possibility for adaptation or migration. Survival became purely a matter of chance based on location and circumstance. Within a 200-kilometer radius, temperatures briefly reached levels comparable to the surface of the sun. Even stone vaporized under such conditions. Between 200 and 800 kilometers, the combined effects of wind, heat, and ground displacement transformed the landscape beyond recognition, leaving nothing alive on the surface. What makes this event so significant in Earth's history is its time compression. Most geological processes that reshape our planet occur over thousands or millions of years, allowing ecosystems to adapt gradually. The Chicxulub impact concentrated change that would normally take eons into minutes and hours, the firestorm, while the shockwave and tsunami devastated regions near the impact site. Something even more catastrophic was unfolding above. The tremendous force of the asteroid collision violently ejected billions of tons of vaporized rock and asteroid material into space. This superheated plume, containing pulverized remnants of both the impactor and Earth's crust, began a deadly journey that would transform our planet's atmosphere into an inferno. As the vapor-rich plume surged upward from Chicxulub, it rapidly expanded beyond Earth's atmosphere. Much of this material, a mixture of solid fragments, molten droplets, and vaporized rock, reached suborbital heights before gravity reclaimed it. What goes up must come down, and in this case, it returned as a lethal rain of fire, like embers from the gates of hell. The returning cloud of debris carried solid, molten, and vapor products that drastically altered environmental conditions, explains Dr. Elaine Markoff, geophysicist specializing in impact events. This triggered a global firestorm unprecedented in Earth's history. Evidence from North America shows entire forests ignited within minutes, with similar devastation recorded in fossil records across Asia and Europe. Computer simulations on screen visualize this phenomenon. Countless glowing particles arcing through the upper atmosphere, their trajectories forming a web of fire encircling the planet. The material began its descent within hours of the impact, turning the sky itself into a heating element. As these particles re-entered the atmosphere, friction transformed them into millions of meteors. The cumulative effect was extraordinary. The upper atmosphere heated to temperatures exceeding several hundred degrees Celsius. Evidence found in the geological record shows this heating occurred simultaneously across continents thousands of kilometers from Chicxulub. The reentry of ejected material caused intense atmospheric heating, which, within hours of the impact, ignited global wildfires across continents, notes Dr. Markoff, gesturing to a world map showing the distribution pattern of impact debris. The global distribution of iridium, a rare element found in asteroids, indicates that ejecta was dispersed worldwide. This heating had catastrophic consequences. As the atmosphere transformed into an enormous convection oven, the thermal radiation ignited dry vegetation across vast regions. Our visualization shows a conifer forest suddenly illuminated by an eerie glow from above. Within minutes, the forest canopy erupts into explosive flames, spreading with terrifying speed. A herd of hadrosaurs, sensing the approaching inferno, abandons their feeding grounds in a desperate migration. The camera follows their flight as the wall of fire advances relentlessly. The slower members fall behind, their fates sealed as the firestorm overtakes them. The evidence for these impact-generated fires is preserved in the KT boundary sediments worldwide, explains Dr. Markoff. We find various forms of carbon, fusinite, soot, pyrolytic polycyclic aromatic hydrocarbons, carbonized plant debris, and charcoal, indicating that fire had swept over continental regions globally. Drill cores from Australia to Argentina contain this distinctive carbon layer, marking a moment when Earth burned. A data overlay appears, showing temperature gradients across the landscape. Near the flame front, temperatures exceed 800 degrees Celsius, hot enough to reduce most organic material to ash in minutes. The fires released massive quantities of greenhouse gases, including carbon dioxide, carbon monoxide, and methane, further destabilizing the already compromised atmosphere. The footage transitions to a mountain valley where a small group of trudentids, feathered, bird-like dinosaurs, seeks refuge in rocky terrain with minimal vegetation. Their adaptive intelligence leads them to one of the few environments that might offer temporary shelter. But even here, the air grows thick with smoke and embers rain down from the superheated sky. What makes these fires different from modern wildfires, Dr. Markoff continues, is their unprecedented scale and simultaneity. Today, even our largest forest fires are limited events. But following Chicxulub, entire continents burned concurrently. There was nowhere to escape. Fossil beds in Montana and Alberta reveal mass dinosaur deaths, their bones preserved in ash layers from this cataclysmic burning. The time-lapse visualization accelerates, showing Earth's transformation. Verdant forests and grasslands wither under the thermal assault before igniting in waves of flame. Within days, lush ecosystems are reduced to charred wastelands, smoking ruins extending to every horizon. Particularly fascinating is the evidence that certain plants were already adapting to this new fire-dominated reality. In several locations in the western United States, ferns were among the first plants to reappear after the impact, Dr. Markov points out, mirroring their pioneering occurrence after modern-day forest fires. But the fires themselves were just one component of a compounding disaster. The soot and ash they generated became atmospheric contaminants, lifted high by convection currents from the fires, joining the existing cloud of impact dust. Our visualization shows these dual processes, the spreading firestorms below and the darkening sky above as particulates accumulate. The once blue sky takes on an ominous yellow-gray hue that gradually darkens to near black. The impact also triggered devastating chemical changes. The impact generated nitric acid rain, which may have persisted for months to years, Dr. Markov explains. Furthermore, when the impact vaporized rocks containing anhydrite, it injected sulfur vapor into the stratosphere. This sulfur produced sulfuric acid rain, a corrosive precipitation that scoured landscapes already ravaged by fire. This may have been one of the more serious environmental consequences, notes Dr. Markov. The combination of fire, atmospheric heating, and acid rain created conditions that few organisms could survive. As the firestorms gradually burned themselves out, they left behind a transformed world. Once lush continents were reduced to ash fields. Wildlife that survived faced new challenges. With plant life destroyed across vast regions, herbivores found no sustenance. The impact vaporized the asteroid and Earth rock, dispersing fine dust particles into the stratosphere and obscuring the sun, explains Dr. Markov. This resulted in dramatic changes to living conditions and brought photosynthetic activity to a halt for several years. Darkness falls. As the last embers cooled across the planet's scorched surface, a more insidious threat was taking shape high above. The atmosphere that once protected life was transforming into its executioner, trapping Earth in a deadly twilight that would challenge the very definition of survival. From space, our blue planet was becoming unrecognizable. The once clear atmosphere now swirled with a lethal cocktail, microscopic particles suspended in the upper air, creating a globally dispersed shroud. This transformation represented a fundamental alteration of Earth's relationship with its life-giving sun. The stratosphere filled with a complex mixture of materials, pulverized rock ejected from the impact site, carbon-rich soot from continental wildfires, and sulfate aerosols formed through chemical reactions. Each component contributed to the unfolding catastrophe, working in concert to block the sun's life-sustaining rays. The impact vaporized significant amounts of both the asteroid and Earth's crust, dispersing an enormous volume of fine dust particles into the stratosphere, explains Dr. Markov. What's fascinating from a climate perspective is how these different atmospheric components interacted to create such profound effects. The smallest particles proved most devastating, while larger ejecta settled relatively quickly within hours to days. The submicron dust and soot remained suspended for months, forming an impenetrable barrier between Earth and the sun. Day transformed into a permanent dusk that stole the sun's warmth. The sky took on a perpetual twilight, like the moment just after sunset when colors drain from the landscape, except this twilight stretched endlessly. Regions that once basked in tropical sunshine now languished in this half-light. Areas farther from the equator descended into darkness reminiscent of polar winter, but without the promise of dawn. Like an endless December night in the Arctic, darkness reigned without the relief of seasonal change. Recent research suggests that a massive plume of micrometer-sized fine dust created a 2-year-long dark period, long enough to trigger catastrophic disruption of Earth's biological systems. The impact on Earth's energy balance was immediate and severe. Without sunlight penetrating to the surface, temperatures began to plummet. The drop averaged about 4 degrees Celsius globally, a single-digit decline that represented a fundamental restructuring of Earth's climate system. A 4-degree global temperature drop represents an extraordinary energy deficit across the entire planetary system, notes a climate researcher examining ice core data. Regional variations would have been much more extreme, with some areas experiencing temperature declines of several tens of degrees. This cooling wasn't distributed evenly. Land masses, especially those in higher latitudes, cooled more rapidly than ocean areas. The temperature differential between equatorial and polar regions collapsed, disrupting atmospheric circulation patterns that had remained stable for millions of years. Rainfall patterns shifted chaotically. Global precipitation declined by approximately 15%, with some formerly wet regions experiencing prolonged drought while others faced unusual deluges as disrupted atmospheric circulation created unstable weather patterns. The damage extended to Earth's protective ozone layer. The impact and subsequent wildfires released massive quantities of chlorine and bromine compounds that efficiently destroyed stratospheric ozone through catalytic reactions. Research indicates the ozone layer may have been reduced by approximately 32%, allowing harmful ultraviolet radiation to penetrate to Earth's surface, adding another stress factor particularly damaging to surface-dwelling organisms and shallow marine life. The combination of darkness, cold, and increased UV radiation created conditions profoundly hostile to photosynthesis, the fundamental energy-capturing process supporting almost all complex life on Earth. Plants and phytoplankton faced an existential crisis. Plant leaves, specialized over millions of years to efficiently capture sunlight, became useless tools in a darkened world. Without sufficient light, the complex biochemical machinery of photosynthesis ground to a halt. In the oceans, phytoplankton populations crashed in the sunless upper layers of the sea, initiating a cascade of starvation through marine ecosystems. The darkness created an unprecedented metabolic crisis across the biosphere. Every calorie of energy in the pre-impact food web traced back to photosynthesis. With that process severely curtailed, the energy foundations of Earth's ecosystems crumbled. Remarkably, new research suggests this impact winter may have been somewhat less severe than earlier models predicted. The asteroid released an estimated 67 plus, or minus 39 billion tons of sulfur, approximately 5 times less than previous calculations indicated, suggesting a milder temperature decline and potentially faster climate recovery. The impact winter was severe enough to cause mass extinction, a researcher notes, but the Earth system proved somewhat more resilient than our worst-case scenario suggested. This helps explain why some lineages managed to survive. The duration of these conditions varied by region and specific effect. The most intense darkness likely lasted between 1 and 2 years, though reduced sunlight and cooler temperatures persisted much longer in some areas. The climate instability triggered a multi-phase extinction event rather than a single catastrophic moment. Sediment cores from this period revealed dramatic changes in pollen types, with ferns and other hardy plants temporarily dominating landscapes that had previously hosted diverse angiosperm communities. This fern spike in the fossil record marks post-catastrophe recovery phases. For animals dependent on plant productivity, the darkness created an insurmountable challenge. Large herbivorous dinosaurs, requiring massive daily intake of vegetation, found themselves in a landscape where plants were actively dying. The specialized adaptations that had made these animals successful for millions of years became liabilities in a world without sufficient plant matter. For the first time in over 100 million years, the basic metabolic equation of dinosaur-dominated ecosystems no longer balanced. The energy required to sustain a Triceratops or Alamosaurus simply wasn't available in the transformed landscape. The planet that emerged from this darkness would be fundamentally different. The complex, dinosaur-dominated ecosystems that had characterized the Mesozoic era were gone forever, replaced initially by simpler communities dominated by opportunistic survivors. Acid oceans and toxic skies. The opportunistic survivors that emerged from the darkness faced yet another existential threat. As clouds eventually formed in the contaminated atmosphere, they didn't bring life-sustaining rain, but instead delivered a corrosive solution potent enough to dissolve rock and shell alike. The planet's chemistry itself had been weaponized against life. When the asteroid struck the sulfur-rich rocks of the Yucatan Peninsula, it fundamentally altered Earth's atmospheric chemistry. The collision vaporized enormous quantities of anhydrite, a sulfur-bearing mineral abundant in the impact zone. This geological quirk of fate proved catastrophic for life, struggling to survive the impact winter. The chemical pathway that followed was devastating, explains Dr. Helen Reeson, environmental chemist at Princeton University. The vaporized sulfur rose into the stratosphere as sulfur dioxide, where it transformed Earth's precipitation patterns into instruments of destruction. Across the planet, once verdant landscapes now stood barren, leaves scorched with acid burns, soil leached of nutrients. High in the stratosphere, sulfur dioxide combined with water vapor, creating sulfate aerosols, microscopic particles suspended in the upper atmosphere with dual destructive roles. While reflecting sunlight back to space and intensifying cooling, they also became the chemical precursors to deadly rain events. As these particles served as condensation nuclei, they seeded clouds with increasingly acidic water droplets. The resulting precipitation delivered dilute sulfuric acid, SO2, plus H2O, plus O2 H2SO4, across Earth's surface. An estimated 67 billion tons of sulfur compounds ensured this acid rain persisted for years. Every raindrop burned vegetation already struggling from lack of sunlight. Leaf surfaces developed visible lesions upon contact. Soil chemistry altered as acid leached vital nutrients and released toxic metals. The atmospheric catastrophe intensified as the impact's tremendous heat shock heated the atmosphere, causing nitrogen and oxygen to combine into nitrogen oxides that reacted with water to create nitric acid, further intensifying the corrosive downpour. On screen, we visualize this through chemical modeling. Sulfur dioxide molecules appear as yellow and red atomic structures, transforming into sulfuric acid. Data overlays show rainwater pH values dropping from the normal 5.6 to as low as 2, comparable to vinegar. What made this acid rain particularly devastating was its global extent. Dr. Reeson continues, as we see footage of a once thriving forest reduced to skeletal trees with chemical burns scarring their bark. Unlike localized industrial pollution today, this was a planetary phenomenon. No terrestrial ecosystem escaped. While land-based ecosystems suffered this acid deluge, marine environments faced an even more insidious threat. The oceans, previously buffered from temperature extremes, now absorbed enormous quantities of atmospheric gases, including sulfur compounds. This triggered ocean acidification at unprecedented speed and scale. For marine life, the consequences proved dire. Calcium carbonate, the fundamental building material for countless organisms, began dissolving in acidic seawater. Creatures that had evolved over millions of years to extract this compound suddenly found their protective structures disintegrating around them. Microscopic plankton with calcium carbonate shells were among the hardest hit. These tiny organisms forming the base of marine food webs declined rapidly, creating a devastating cascade effect. As plankton populations crashed, animals that fed on them starved, disrupting the food web from the smallest zooplankton to the largest predators. We can see evidence of this devastation preserved in seafloor sediments. Dr. Reeson explains, as we examine core samples showing a stark absence of calcium-rich remains. This calcite gap, reveals how completely marine ecosystems collapsed. Particularly affected were the ammonites, shelled cephalopods that had thrived for over 300 million years. Their shells, composed primarily of aragonite, a form of calcium carbonate particularly vulnerable to acidification, literally dissolved before their soft bodies could adapt. After weathering countless environmental changes, this chemical assault finally ended their 300 million year dynasty. Our visualization shows a split screen. Acid rain falls on a struggling fern, causing visible damage to its fronds. Simultaneously, the intricate shell of a foraminifera disintegrates in acidic seawater, its structure collapsing in real time. This dual acidification, sulfuric acid rain on land and carbonic acid formation in oceans, created a uniquely destructive extinction mechanism operating at the chemical level of life itself. In the fossil record, we see entire taxonomic groups vanish from both land and sea simultaneously. The acidification crisis eventually subsided as sulfur compounds precipitated from the atmosphere and oceans slowly neutralized. But irreparable damage was done. The collapse of shell-forming organisms had interrupted Earth's carbon cycle. The ocean floor normally accumulates carbonate minerals as marine organisms die and sink, sequestering atmospheric carbon. This vital planetary process was disrupted, further destabilizing climate systems. In a cruel twist, the long-term aftermath included a greenhouse warming phase. As dust and sulfate aerosols settled, carbon dioxide released from impact-triggered wildfires and dying vegetation remained for thousands of years, causing temperatures to exceed pre-impact levels. Life that had adapted to survive cold now faced unusual warmth. This environmental whiplash, from impact heat to winter to acid crisis to greenhouse warming, created sequential extinction filters. Each phase eliminated species that had survived the previous catastrophe. What's particularly fascinating about this extinction mechanism, notes Dr. Reeson, examining a fossilized leaf with acid burn patterns matching those in modern industrial zones, is how it operated simultaneously across all Earth's environments. The same chemical processes affecting land were mirrored in marine systems through different pathways. This global synchronicity of acidification left almost nowhere for life to hide. The Great Dying, this chemical catastrophe, represented just the beginning of a biological unraveling that would play out over months and years. The synchronized global acidification served as the deadly prelude to what paleontologists now recognize as one of the longest-running extinction events in Earth's history. While the initial impact and firestorms killed countless creatures instantly, what followed was an ecological collapse that progressed with a terrible, methodical efficiency. Across the transformed landscape, the first victims were those most directly dependent on photosynthesis. The darkness effectively severed the base of the food web. Plants that had survived the initial conflagration now withered in darkness, their energy reserves depleted. In marine environments, the microscopic phytoplankton that had supported vast oceanic ecosystems vanished. This was a quieter, more insidious form of death, starvation on a planetary scale. The disruption created a domino effect through trophic levels. A Pachycephalosaurus, once robust and territorial, now appears gaunt as it searches fruitlessly for edible vegetation in a barren woodland. Its distinctive dome head, evolved for competitive headbutting rituals, serves no purpose as social structures collapse under the pressure of hunger. These specialized herbivores were among the first dinosaur groups to show population decline, their bodies unable to process the limited acid-damaged plant material that remained. The extinction pattern reveals a stark but uneven timeline. Fossil evidence indicates that some populations vanished within weeks to months following the impact, while others managed to persist for years before ultimately succumbing. This reflected specific vulnerabilities rather than random chance. What we're seeing in the fossil record is a complex pattern of extinction that directly correlates with ecological position and physiological adaptability, explains our paleontologist. The extinction rates vary dramatically across different animal groups, with certain marine organisms like rays experiencing catastrophic losses, while other groups like sharks showed more resilience. This presents us with a fascinating scientific puzzle about what factors determine survival. Like the final acts of a planetary tragedy, the fossil record tells a story of systematic decline. On a scientific overlay, we can see that approximately 75% of all species on Earth perished, an almost incomprehensible level of biological devastation. The chart breaks down extinction rates across various animal groups, revealing how the event disproportionately affected certain lineages while sparing others. The devastation was particularly profound in dinosaur ecosystems. A once mighty Tyrannosaurus, apex predator of its age, wanders an increasingly barren landscape. Its powerful jaws and serrated teeth, perfectly evolved for dispatching large prey, become increasingly useless as herbivore populations crash. The predator's deteriorating physical condition, protruding ribs and dull, patchy skin, reveals how metabolic demands that had been an advantage in the resource-rich pre-impact world became a fatal liability. Velociraptors, those intelligent pack hunters that had dominated the mid-sized predator niche, faced similar challenges but with a different adaptive response. Their smaller size and potential for coordinated hunting initially allowed them to target remaining small prey more efficiently than larger predators. But as weeks turned to months, even these adaptable hunters found fewer targets. A scene shows a raptor pack splitting up, social bonds breaking down as individualistic survival instincts take over. This extinction attacked multiple environmental systems simultaneously. Terrestrial, freshwater, and marine ecosystems all face their own versions of collapse, though through slightly different mechanisms and timelines. The land-dwelling dinosaurs faced immediate challenges from the impact, winter, and loss of plant life. Our expert continues. But marine reptiles like mosasaurs experienced a more gradual decline as ocean acidification and plankton collapse worked their way up the food chain. This created a situation where different species faced their extinction moment at different times, but with the same inevitable outcome. The fossil record shows evidence of this staggered die-off. A time-lapse visualization demonstrates how certain groups disappeared almost immediately, while others showed a more gradual decline over months or years. Most striking is how the extinction preferentially targeted larger animals, a pattern consistent with resource limitation. Among the dinosaurs, size became a critical factor in determining extinction timelines. The largest sauropods, despite their plant-based diet, had evolved efficient digestive systems that could process lower-quality vegetation. This initially gave them an advantage over more specialized herbivores. But their enormous caloric requirements eventually became unsustainable as plant productivity remained suppressed. What's particularly striking is how this extinction event differentially affected various animal groups. While all non-avian dinosaurs ultimately perished, other seemingly vulnerable species showed remarkable resilience. Slow-moving tortoises, environmentally sensitive frogs, and the seemingly fragile ancestors of modern birds somehow endured the same conditions that wiped out the dinosaurs. The visualization shifts to focus on a dinosaur that appears relatively healthy compared to others. A small, omnivorous dinosaur capable of eating anything from insects to carrion to plant material. Its dietary flexibility provides a temporary advantage, but the fossil record confirms that even these adaptable dinosaurs eventually disappeared. There's something profoundly moving about witnessing the final chapter of creatures that had dominated Earth for 165 million years. These magnificent animals, from the towering sauropods to the fierce predators, all succumb to the same implacable forces. Their extinction stands as a somber reminder of life's fragility, how even the mightiest can fall when Earth's systems are disrupted. In stark contrast, we see glimpses of the creatures that would survive. Small mammals scurrying beneath the debris, covered in insulating fur that helps them endure the cold. Their burrows provided shelter from temperature extremes. Their omnivorous diets allowed them to exploit whatever food sources remained. and their small body size meant they required far fewer calories to sustain themselves. In their survival lay the seeds of a new era, proof that the survivors, however as the devastated, last dinosaurs would find their final breaths. A remarkable transformation was already beginning underground. The very adaptations that made these small mammals appear weak during the age of dinosaurs, their tiny size, their need for shelter, their unspecialized diets, became the unexpected keys to inheriting the planet. While 3/4 of Earth's species vanished in the apocalypse, these survivors would become the architects of our world's next great evolutionary experiment. The KPG mass extinction that occurred 66 million years ago may have claimed the mighty non-avian dinosaurs, but it was remarkably selective in its destruction. When we zoom in on the evolutionary tree, we discover that approximately 76% of species perished, leaving a critical remnant that would repopulate the planet. Specific traits and adaptations determined which creatures would survive to reshape Earth's future. Among the mammals scurrying beneath the debris, several adaptations proved critically important. Their small body size, predominantly mouse to shrew-sized, meant they required far fewer calories to sustain themselves in a world where food had become desperately scarce. Simple mathematics favored these miniature survivors. A 5-gram mammal could survive on insects and seeds in a devastated landscape, while multi-ton herbivores needed vast quantities of vegetation that no longer existed. Looking at the fossil record, we see a heterogeneous pattern of extinction, explains Dr. Samantha Wright, paleobiologist specializing in mass extinction events. Taxa with large geographic ranges showed higher survival rates, as did those adapted to high-latitude settings. Her research reveals a profound truth. Amid global devastation, the tiniest creatures, those most overlooked during the dinosaurs' reign, became the bearers of life's future, carrying the genetic legacy that would eventually lead to our own existence. The darkness that engulfed Earth created unique survival challenges, yet some animals were pre-adapted to navigate in low-light conditions. Snakes could continue hunting effectively even in the darkness that followed the impact, using their heat-sensing pits and ground vibration detection to locate prey. For many mammals, burrowing behavior became their salvation. These underground sanctuaries provided more than simple shelter. They were miniature arks preserving life while chaos reigned above. Within these earthen chambers, temperatures remained stable while surface conditions swung wildly between scorching heat and freezing cold. As toxic rain fell and wildfires raged across the barren landscape, these humble burrows became the cradles of Earth's future biodiversity. When examining the early recovery ecosystems, we see an unprecedented opportunity unfolding for these survivors. With the extinction of non-avian dinosaurs, ecological niches that have been occupied for over 160 million years suddenly became vacant. This created what evolutionary biologists call ecological release, the removal of dominant competitors, allowing previously marginalized species to explore new evolutionary possibilities. Marine environments tell a particularly interesting survival story. While specialized feeders experienced extinction rates exceeding 72%, their non-specialized relatives fared significantly better. Sharks, with their dietary flexibility and wide geographic distribution, weathered the extinction far more successfully than many other marine predators. Dietary flexibility emerges as another crucial survival factor. Omnivorous mammals that could consume anything from insects to seeds to carrion had a distinct advantage over specialized feeders. When particular food sources disappeared, these generalists simply switched to whatever remained available. Not being picky eaters became an evolutionary superpower in a world where food chains had collapsed. The extinction crisis also created unexpected side effects that would shape Earth's future in profound ways. As forests recovered in the absence of giant dinosaurian herbivores, they grew thicker, blocking sunlight from reaching the forest floor. This environmental change triggered an evolutionary response we can trace through the fossil record: the development of larger seeds and fruits. The extinction of sauropods fundamentally changed forest ecosystems, explains Dr. Wright. Without these ecosystem engineers consuming vast quantities of vegetation, forests grew denser, creating selection pressure for larger fruits and seeds. These evolutionary developments would have far-reaching consequences. The larger fruits that evolved in these post-dinosaur forests became primary food sources for many animals, including our own primate ancestors. In this way, the extinction event indirectly shaped human evolution through its effects on plant communities. About 35 million years after the extinction, seeds began getting smaller again as large land animals once more became sufficiently numerous to impact forest structures. This evolutionary shift demonstrates the dynamic interplay between animal communities and plant evolution throughout Earth's history. Among the survivors, we see the early stages of adaptive radiation, the process by which a single lineage diversifies to fill many ecological roles. The mammals that weathered the apocalypse would eventually radiate into bats, whales, primates, and thousands of other forms, exploring new possibilities in the ecosystem spaces vacated by dinosaurs. The fossilized remains from this period reveal another surprising pattern. High-latitude species generally survive better than their tropical counterparts. The ability to endure seasonal temperature fluctuations apparently pre-adapted these organisms to withstand the rapid climate changes triggered by the impact. Perhaps most remarkable about this survival story is its connection to our own existence. Had the asteroid missed Earth or struck in a different location without the sulfur-rich rocks of the Yucatan, the extinction pattern would have differed dramatically. The ecological opportunity that allowed mammalian evolution to accelerate, the opportunity that eventually produced primates and humans, might never have occurred. The study of the KPG boundary and the Chicxulub crater reveals the conditions that make new evolutionary possibilities emerge. The very catastrophe that ended one evolutionary experiment created the conditions for another. Our understanding of this pivotal moment continues to evolve as scientists develop new methods to extract information from the geological record. As the first green shoots emerged from the ash-covered soil, the survivors began the slow process of reclaiming the planet. What would follow was not a return to the world that had existed before, but something entirely new, a mammalian revolution that would ultimately lead to the world we know today. Rise of the mammals. This mammalian revolution would unfold at a pace invisible to any single observer, but when compressed into evolutionary time, reveals perhaps the most profound transformation Earth has ever conducted. The disappearance of dinosaurs ended one chapter of life's story and opened an entirely new one where small, furry creatures would gradually inherit the planet. In the recovering forests that emerged from the ash-covered soil, something revolutionary was happening. The ecological vacuum left by extinct dinosaurs created unprecedented opportunities for the survivors. The small mammals that had once scurried in the shadows of giants now found themselves in a world of possibilities. The extinction event created the ecological opportunity for mammalian evolution that eventually led to primates and humans, explains Dr. Miranda Chun, evolutionary biologist at Cambridge University. This was the redirection of life's trajectory on Earth. Initially, mammals remained relatively modest in both size and diversity. The fossilized remains from the Paleocene epoch, spanning from 66 to 56 million years ago, show the first tentative expansions. These early post-extinction mammals generally maintained the small body sizes that had helped their ancestors survive, but they were already beginning to explore new ecological possibilities. The absence of dinosaurs transformed both animal life and plant communities. With giant herbivorous dinosaurs no longer browsing the treetops or trampling undergrowth, forests grew denser. The relationship between plants and animals entered a new phase of coevolution that would prove crucial for primate development. The visual evidence of this transformation appears in the fossil record through a remarkable shift in seed and fruit structures. Without large dinosaur herbivores to disperse massive seeds, plants began producing smaller seeds. However, these fruits grew larger and more nutritious over time, an adaptation to attract the new seed dispersers. mammals, and birds. These developing forest ecosystems, with their closed canopies and abundant fruit resources, created ideal conditions for a particular group of mammals that would eventually include our own ancestors. The early primates found advantages in developing specialized adaptations for life in these new forests. As we move into the Eocene epoch, approximately 56 to 34 million years ago, the fossil record shows an acceleration in mammalian diversification. What had begun as subtle variations among small, generalist mammals became an explosion of specialized forms. Herbivores, carnivores, burrowers, climbers, gliders, and even the earliest marine mammals emerged, each exploiting different aspects of the post-extinction world. Among these emerging mammals, the early primates developed specific adaptations that distinguished them from their relatives. Enhanced visual acuity allowed them to judge distances precisely when moving through branches. Their growing manual dexterity, with opposable thumbs and flattened nails instead of claws, enabled them to manipulate objects with increasing precision. Most critically, these early primates were developing dietary preferences that would shape their evolution. The abundance of energy-rich fruits in the recovering forest provided a premium food source that rewarded those individuals with the best ability to locate, grasp, and process these nutritional packages. This relationship between fruit evolution and primate development is a significant example of how the extinction event indirectly shaped the course of evolution, notes Dr. Chun. The very foods that sustained our earliest ancestors existed in that form specifically because dinosaurs had disappeared. The timeline of this transformation reveals the gradual, yet inexorable pace of evolutionary change. By compressing millions of years into minutes, we can visualize mammals growing from mouse-sized creatures hiding in burrows to diverse forms occupying every available niche in the recovering ecosystems. The initial diversification appears in the Paleocene fossil record, with numerous new mammalian groups emerging. The Eocene then witnessed further radiation and the appearance of recognizable primate forms. On screen, we see a scientific overlay showing this timeline with key evolutionary milestones. Arrows branch outward from the small surviving mammals, gradually expanding to fill the vacant ecological spaces. One particular branch leads toward early primates, with visual markers highlighting the development of grasping hands, forward-facing eyes, and larger brains, all adaptations that would eventually lead to human evolution. What's particularly striking about this mammalian takeover is how it contrasts with the previous Mesozoic power structure. For over 160 million years, dinosaurs had dominated terrestrial ecosystems, while mammals remained peripherally important. Within just 10 million years after the impact, a geological eye blink, mammals had diversified into forms that would have been impossible in a dinosaur-dominated world. The forests themselves were changing in ways that supported this mammalian revolution. Without massive herbivorous dinosaurs browsing canopies and trampling undergrowth, forest structures became more complex. Multi-layered canopies created diverse habitats within a single forest. This three-dimensional complexity offered numerous ecological niches for climbing, leaping, and fruit-eating mammals. Dr. Chun explains further. The shift in forest structure from open to closed canopy was a direct consequence of the loss of large herbivores. This created new habitats and food sources, which drove the diversification of mammals, particularly the early primates. This evolutionary narrative raises a profound question. Would humans exist today if the asteroid hadn't hit? The scientific consensus suggests probably not. The dominance of dinosaurs had effectively constrained mammalian evolution for over 160 million years. The nocturnal, insectivorous lifestyle that had allowed mammals to coexist with dinosaurs had become an evolutionary cul-de-sac, limiting their potential diversification. The asteroid impact eliminated competitors and fundamentally restructured Earth's ecosystems in ways that specifically favored the adaptations our ancestors would eventually develop. The primate combination of grasping hands, depth-perceiving vision, and expanded brains found its perfect expression in fruit-rich forests that only existed because dinosaurs had vanished. As this evolutionary phoenix rose from the extinction's ashes, the ancestral forms that would eventually lead to monkeys, apes, and humans were developing in these recovering ecosystems, still benefiting from the ecological opportunities created by the extinction event millions of years earlier. Life's story is written by moments of cosmic chance and the slow march of evolution. The asteroid that erased the dinosaurs' reign represents evolutionary contingency at its most dramatic, a random cosmic event that rewrote Earth's future. Had that asteroid missed our planet or struck elsewhere, we'd be living in a fundamentally different world, if we existed at all. Non-avian dinosaurs might still dominate today's landscapes, and the evolutionary path leading to humans would likely never have unfurled. Our mammal-dominated planet stands as testament to this interstellar dice roll that forever altered life's trajectory, an unexpected beginning